Hello, my name is Peter Jarrett. This is going to be a practical demonstration of transformer vector groups and what happens when you reverse phase sequence or rotation to a transformer. On the bench here, we've got a Manta 5100 that we're going to be using as a voltage source. We've got a Megger PMM2 that's going to be our phase angle meter to show the displacement between the primary and the secondary windings. We've got 3 single-phase transformers that right now are connected 160 turns on the primary, 80 turns on the secondary. At the moment, it's Y on the primary and an AC delta on the secondary. We are going to connect them, or they are connected, exactly as shown on this nameplate that we'll go over in a second. It's a YND1. We're going to go ahead and we're going to apply normal ABC or 1, 2, 3 phase sequence to. We're going to measure the output and prove that it matches the nameplate. And we're going to go ahead and switch up the applied phase sequence to ACB or 1, 3, 2 and observe what we observe. All right, let's move on. All right, here's the transformer we're going to build for our example out of the single phase transformers on the bench. It is a YND1 transformer. The high side is Y, the low side is a delta or an AC delta to some. H0, H1, H2, H3, X1, X2, X3. Here's the vector group diagram. And H1, H2, H3, X1, X2, X3. So if we were to draw a clock here with 12 o'clock being on my H1 and an overlap or overlay the X on top of that, you would see that the X1 is at 1 o'clock, hence the YND1. Here is the IEC diagram for that. And we're just going to use that to build up the transformer. And you can see the windings 1, 2, and 3, 1, 2, and 3, and spot, non-spot, and how they're connected. So let's get to the transformer construction. All right, transformer setup. So you'll notice we have 3 single-phase transformers. I've labeled them 1, 2, and 3. Right now they are 160 turns on the primary, 80 turns on the secondary. You can see where the spot is and spot. High side, red, yellow, blue, going to the Manta as A, B, and C. This outer set of leads here, the red and the black, is going to the A channel of the Megger PMM2. So we're taking a phase-to-phase voltage to the Megger for the high side reference. Low side, this set of leads, the red and the yellow, are going to channel B of the Megger. Again, it's a phase-to-phase quantity, 1 to 2 or A to B. So the next thing is we need to make up that AC delta. So we're just going to copy this nameplate. So I have 3 jumpers, and we're going to follow along with what it shows here. So inserting the jumper into spot of 1, and that is going to go to non-spot of 3. Next one, spot of 2. To non-spot of 1. Last one's going from spot of 3 to non-spot of 2. You can pause it for a second, take a look at it if you want to. So, keeping with the nameplate that we showed earlier, this will now be H1, H2, H3, any one of these will be HO, and then we have X1, X2, and X3 of the delta. All right, let's apply. So again, we are A, B, C phase sequence. We're going to go ahead and apply. We're applying 14 volts, phase to neutral, on the Y winding, the high side. And so over to the phase angle meter. we've got 24.25-ish volts phase to phase, which works out. That's 14 times the square root of 3. On the secondary winding, we're seeing just about 7 volts, which is about what we expect. The phase angle is almost exactly 30 degrees. And if you can see it here, the yellow is the secondary winding and the red is the primary winding. So the secondary winding is lagging the primary winding by 30 degrees, which is what we expect, and it matches up with the nameplate. So let's go back to the test gear. I'm gonna go ahead and turn it off. We're gonna flop that rotation. Oops. And turn it back on again. And gonna come back over here. Didn't change any leads. Same thing, it's about 14 volts times the square root of 3 and 7 volts on the secondary and almost exactly 330 degrees lagging. The secondary is lagging the primary by 330 degrees or leading by 30, depending on how you like to think about it. Here's the primary in red, secondary in yellow. So all we did was flop the phase sequence. All right, here's the nameplate of the transformer we just built and demonstrated with all positive and all negative sequence. So here's the vector group on paper, and here it is on transparency. So we can see H1, H2, H3, X1, X2, X3, and same up here. So in this case, the secondary lags the primary by 30 degrees. Now, if you were to take the same transformer and apply backwards phase sequence to it, you basically invert the nameplate. It's almost like you're looking at it from the back. So H1, H2, H3, X1, X2, X3. And you could see that if you were a little stick man standing where this stick is and this was rotating, it would be 1, 3, 2 phase sequence. Now, same transformer constructed the exact same way, the secondary leads the primary by 30 degrees or lags by 330 degrees. So what does a utility do when they are ACB phase sequence? In the case of the utility I work for, the utility strives to put the utility A phase on H1, the utility C phase on H2, and the utility B phase on H3. And that way, with an ACB phase sequence, we still have a 1, 2, 3 phase sequence, holding the vector group true that's on the nameplate.